So here's what the central limit theorem says now. We start off by talking about these things that we call sampling distributions. All right. And I'll give you an example what a sampling distribution is. In a sampling distribution, if I ask you for the average height of all people at your school, right? Average height of all people at your school. In order to find the average height, what we have to do? What we have to do to find the average height? Anybody can tell me that?
You'd have to have the height of the people.
Of all the people at the school, right? Can we find that average height? Maybe. But what do we do instead of trying to look at all the people? We try to look at a what? Instead of looking at everybody, we try to look at
Sample.
a sample, right? And so what happens is we're going to go inside classrooms, for instance, and look at 10 people in every class and find their average height, right? And the value that we get should be fairly close to the average height of the entire population. That's the thought there, right? Now, here's what's going to happen though. If I go from class to class looking at 10 people finding average heights, will all those average heights be the same? Yes or no?
No.
Good. No. Let's say I only have 5 classrooms, right? And those 5 classrooms have, let's say they each have 30 people in them. If I go take 10 different people out of those 5 classrooms, right? I'm gonna get 5 different statistics. 5 different statistics. And the statistic comes from a sample. I'm gonna get 5 different ones, right? They're not gonna be the same. They may be the same, but they probably won't be the same. Well, the sampling distribution says this. If I look at every possible sample of size 10 from those 5 different classrooms, every possible sample of size 10 from those 5 different classrooms, I can form a probability distribution of that. And so this is the probability distribution of a statistic. A statistic. A statistic always comes from the sample. It always comes from the sample. It is an estimate of the population. When samples of size n, in our case, our n was 10, and we repeatedly take samples of size 10 and form every possible sample there is of size 10, we get what's called a sampling distribution. We look at the sampling distribution of X bar, the sample mean. We're gonna look at the X bar or the sample. This is a sample statistic. It's coming from the sample. So we're gonna look at that, the sample mean, which we call X bar. Here's an example of what I mean. A new startup company is composed of the following employees. Their years of experience with the company are listed. So you have Jen, who has 1 year, Sean, who has 3, Tim, who has 5, and Carol, who has 7. What is the mean number of years worked for these employees? If I asked for the mean number of years worked for these employees, what would you do? How would you find the mean of these values?
Add them all up and then
Add them
divide
all
by
up. So
4.
mu of x is equal to 7, 5, 3, and 1. That's 12. That's 16. That's 16 divided by 4. So the mean is 4, right? What's standard deviation equal to? How would you find that? Sigma x will be, you take each one of these, subtract it from the mean, square that. I'm going to actually plug this to a calculator and get that value for y'all real quick. The mean standard deviation here is 2.236, we'll say. 2.236. So that's standard deviation for this particular thing, all right? So you have an average of 4 years, that's going to vary by about 2.236 years. Now, here's what I can do then. What if I created every possible sample of size 2 between these 2 employees, right? If I created every possible sample of size 2 between these 2 employees. Here's what we have again. Jen has 1 year. Sean has 3 years. Tim has 5 years. And Carol has 7 years. I'm going to create every possible sample of size 2 with replacement. It means I'm going to take a person out, put them back in, take a person out, and I'll have my size 2 sample, all right? So if I do this right here, if I take Jen out, right? She has how many years of experience?
1.
1. Put her back in and take her out again. I get this sample that has a average, a sample mean. What's 1 plus 1?
2.
And I'm going to divide that by 2. So 2 divided by 2 is 1. Jen and Sean would have 1 and 3. So it's 1 plus 3, that's 4. 4 divided by 2 is 2. Jen and Tim, 1 and 5. 1 plus 5 is 6, and 6 divided by 2 is 3. Jen and Carol, 1 and 7. 1 plus 7 is 8. 8 divided by 2 is 4. These are all possible. These are all the possible samples where Jen is the first person taken out. Right? The next one should actually be Sean and Jen. I messed that up. Sean and Jen here. Right? And Sean and Jen would have this right here. Sean has 3 years. Jen has 1 year. 3 plus 1 is 4. 4 divided by 2 is 2. 3 and 3. So both Sean and Sean. So that'll be 3 plus 3 is 6. 6 divided by 2 is 3. Hope you can pick up on this. You're going to get this sample 2, 3, 4, 5. Tim and Jen, that is 5 and 1, 6. So that's 3. 5 and 3. So that's 5 plus 3 is 8. 8 divided by 2 is 4. 5 and 6. And then Carol would be 7 and 1. 8. 8 divided by 2 is 4. Carol and Sean, 7 and 3. 7 plus 3 is 10 divided by 2 is 5. So that's 4, 5, 6, and 7. Here's what we've done. We've looked at every possible sample of size 2 that you can take here. Every possible sample of size 2. There are no other samples of size 2 that I can take here. I've looked at every possible, I exhausted those. There are actually 16 possible samples of size 2 that I can take. And I've given you all 16 of them. We've created what's called the sampling distribution. And we've looked at the sample mean for each one of these things. What do we call the sample mean again? What's the sample mean? What's the sample mean called? X bar. This is called X bar.
X bar.
Yeah, that's called X bar. So the sample mean, we looked at every X bar that was possible for this sample, every X bar that was possible. Here's what I want to know. I want to know, what is the population mean for all of the X bars? What is the population mean for all of the X bars? What am I asking you to do?
Add them all up.
Add them all up and then divide by the total, right? If you add all these up, guess what number you get? If you try to do it, it's equal to 64. You divide that by the total, which is 16 total samples. 64 divided by 16, guess what that's equal to? That is equal to 4. Come back over here. What was the mean of these 4 numbers right here? It was also what number? 4. This is not a coincidence. This happens all the time, actually. All right, this happens all the time. The mean of the population, which we call mu, is also equal to the mean of all of the sample means. The mean of the population, which we call mu, is always equal to the population mean of all the sample means. All right. The standard deviation of this sample, I'll calculate that too for you, by the way. That's 1. Let's see. Stat, edit, clear 1. There. Standard deviation of this sample, calc 1 bar, 702, is equal to 1.5811. Standard deviation of this sample, the standard deviation of the X bars, the population is equal to 1.5811. If you come back to our standard deviation of the actual thing, the actual standard deviation of the population was 2.236. If we do some magical math here and we do that number, then we do 2.
So it's half of it?
If we do 2.23, it's not actually half, and we divide it by the square root of 2, which was the sample size, we get 1.5811 again. We get 1.5811. So what this tells me is that this right here, this is also not a coincidence, by the way. I literally took the population standard deviation, which was 2.236, divided it by the square root of my sample size, and I got this new standard deviation, which you saw I calculated the standard deviation by hand too as well, and got 1.5811. So this is going to lead us then to what we call essential limit theorem, right? And essential limit theorem basically says this: if I take every one of those particular sample means that I got, if I take every one of those sample means that I got, here they go again, by the way, I got a 1, I'm going to make a dot plot, a 2, a 3, and a 4. That's when Jen was first. The next one was when Tim was first, or when Sean was first. You got a 2, a 3, a 4, and a 5. Then you got Tim first. You got a 3, a 4, a 5, and a 6. Then you got when Carol was first. You got a 4, a 5, a 6, and a 7. That's what the dot plot of this looks like. When I look at this dot plot, what shape do you notice it to be? Don't say a triangle.
A bell curve.
It is a bell curve. Thank you so much. It is approximately normal. It is actually very normal, to be honest. What's the mean of the curve?
4.
4. So we notice that the shape is a bell. The mean is equal to 4. And the standard deviation is going to be equal to 1.5811, or whatever that was a second ago. These are not coincidences, by the way. This is how statistics really works when we start looking at the math. So what I'm developing then is what we call the central limit theorem. And the central limit theorem says this: we call it CLT, and it states that the sampling distribution of a sample means. What do we call the sample mean again, by the way?
X bar.
X bar. The sampling distribution of the sample means will be approximately normal when the sample size n is greater than 30. It will be approximately normal when n is greater than 30. And what it says is the mean of the sampling distribution of the sample means is the mean of the population. So mu of X bar, what does that stand for again? Mu stands for, in case you forget this, mu is equal to the population mean. That is the population mean. Mu of X bar is the population mean of the sample means. That means I've added up every sample mean. It is equal to mu of X, which is this right here, mu of X, the population mean. Mu of X bar is equal to the mean of the population. I can use the sample means as a rough estimate for the mean of the population. The standard deviation of the X bars, also known as what we call now the standard error. And I'm going to tell you why it's called the standard error after I write the formula out. The standard deviation, sigma X bar, is now equal to sigma X. Again, this is the population standard deviation divided by the square root of n. Anytime we divide something by the square root of n, we're talking about a standard error. So we're taking the standard deviation. We can't call this again a standard deviation. This is a totally different thing. Standard deviation is this symbol right here. Because we're dividing it by the square root of n, we get a new thing called the standard error. But the standard error is really just a standard deviation. Now, this only works when n is greater than 30. This only works when n is greater than 30. You might be saying, well, when we just did that last example, n was only 2. And it worked. Why did it work when n was only 2, which is significantly less than 30? Well, if it's not less than 30, it can also work if the distribution from which you're drawing from is already normal. And these numbers, 1, 3, 5, and 7, when you distribute them like this in terms of size 2, look what shape they gave me. They gave me an already normal shape. So the distribution I was pulling from was already normal. So the central limit theorem also holds there. If it's not bigger than 30, this bigger than 30 part right here, by the way, so we call our sufficiently large. That means that the distribution is sufficiently large. If it's not sufficiently large, you can still do it as long as the population from which the sample is drawn, it doesn't say, if the population from which the sample is drawn, it should be, is already normal. I missed that part, you guys. Write that in there. Is already normal. So the distribution from which you're already drawing from is normal, then you can still use this. So let's see how we apply this.
Well, Professor,
Yes, ma'am.
what does CLT mean?
Central limit theorem.
Okay.
All right, so decide the following scenario meets the conditions for CLT, central limit theorem. If it does, find the mean and standard deviation of the sampling distribution. Here's what we're going to do. We're looking for one thing. We're looking for a sample size. And the magic number for our sample size is anything bigger than 30. So I say cell phone bills for residents of a city have a mean of $47 and a standard deviation of $9. Random samples of 100 cell phone bills are drawn from the population. Find the mean and standard deviation of the sample means sampling distribution. They want us to find a sample means sampling distribution, by the way. What do we call the sample mean again?
X bar.
X bar.
This is X bar, good. So we're looking at X bar. So this already tells me I'm going to probably talk about central limit theorem. But the first thing I have to do is identify the sample size. What is my sample size?
100.
100. Random samples of 100 cell phone bills. So my N here is equal to 100. What's significant about that? N is greater than or equal to 30. Because N is greater than or equal to 30, by central limit theorem, by CLT, the X bars will follow a normal distribution. It's how I write the parameters of the normal distribution. A normal distribution has two parameters. What are they? A normal distribution. What do I need to draw a normal curve? What two things do I need to draw a normal curve? I need a what?
The mean and a standard deviation.
Good. So we now have a mean and a standard deviation that follow like this. The mean for this particular distribution is going to be the mean of the population, which in this case is $47. They tell me a city have a mean of that right there. So the mean is 47. And the standard deviation is going to be whatever the standard deviation of the population, in this case 9, divided by the square root of N. And so 9 divided by the square root of N, well, 9 divided by the square root of 100 is just, this value is just 0.90. And here's what this says then. When we look at one person's cell phone bill, the average should be about 47. But that's going to deviate from that average by about $9. That can deviate from the average from about $9 when we look at one person. When we look at 100 people's cell phone bills, though, and we look at that average should be 47, and it's only going to deviate by about 0.9. Why is the standard deviation so much lower for 100 people than it is for one person?
Is there more values?
Good. And what do you mean by there's more values? There is more values. What do you mean by that? What does standard deviation measure again? What does it measure?
Average deviation from the
It's
mean.
the average deviation from the mean, right? Here's what happens. As you take more values, what should happen to that average deviation, though? In theory, what you're doing, it should be smaller because your samples are getting larger. And when your samples get larger, they start to look more like the population. And when they look more like the population, then we'd expect those values to go to their true values. So the standard deviation should be decreasing as you move up. Hey, my computer's about to die and I do not have my charger. I am going to have to stop right here. I'm going to have to stop right here, you guys. I will finish these notes on, I'll finish these notes next time I see y'all, all right?
All right.
All right.
All right,
Thank you.
y'all have a good night.